everybody, this is our video on inverse derivatives. Now you already watched a video on how to do the derivative of inverse trig functions like arcsine, arccosine, arctangent. But what if you want the derivative of just a regular inverse function that's not necessarily an inverse trig function, like all the other functions out there? So this video is going to show you how to do the inverse of any function, even if you don't necessarily have an equation to do an inverse of. Okay, so before we do anything with inverse derivatives, let's just review quickly inverse functions, okay? Like in general, what's the deal with inverse functions? How do they work? And this is all going to be review for you, but I need to make sure you remember all this because you're going to use some of it whenever you do your inverse derivatives. Okay, so jot this down here. When you have a function, the inverse, this notation you've seen before, f to the -1, that means the inverse function. Conceptually, a function and its inverse will undo each other. That's generally what happens when you do them. Now, this is vertical line test, and this is horizontal line test. So if a graph passes the vertical line test, we already know that means it's a function. If it passes the horizontal line test, that means its inverse is a function. So like the absolute value of x, this function does not pass the horizontal line test because more than one point hits a horizontal line. But something like this does pass the horizontal line test. This also passes the vertical line test. If a graph passes a vertical line test and horizontal line test, then it is called one-to-one. Typically, it's abbreviated 1-1, a one-to-one function. So that means the function is an inverse. The function and its inverse are functions. Okay, so graphically, all right, so graphically, whenever we have graphs here, there are going to be reflections over the line y equals x. So let's take a look at a couple graphs here. I think one graph will do it. One of the more common ones here, and while we do it, we'll also talk about numerically, which has to do with tables. Whenever you have a table of an inverse and its functions, x and y switch roles. That just means x and y are going to be opposites. So if we have a normal f of x, and let's do the inverse, x, y. Okay, let's do my favorite one, e to the x and natural log of x, because you can never see this enough times because people love to forget what natural log of x looks like. So e to the 0 is 1, e to the 1 is e. Let's do -1, that'd be 1 over e. I remember e is like 2.7, so 0, 1, 1, so like 2.7. -1, 1 over 2.7 is like a little less than, it's like around 1/3, we'll say. You could do 2, that'd be e squared, so like 2.7 squared. I don't know what that is exactly though, so I'm not even going to try to plot that nicely, but okay, we know this has a horizontal asymptote of y equals 0. All right, so remember, because the inverse swaps ordered pairs, I can get them right away. Instead of 0, 1, it's 1, 0. 1e becomes e1. 1 over e is -1, and e squared is 2. So let's plot natural log in pink. All right, 1, 0. E, so 1, 2, 2.71. So plot this with me here. 1 over e for x, -1, and that shall do it. So instead of a horizontal asymptote, I have a vertical asymptote of x equals 0. All right, and again, every function and its inverse will be reflections over the line y equals x, which is this line with a slope of 1 and a horizontal, or what am I saying? A slope of 1 and a y-intercept of 0. So y equals x. All right, and the x and y values swap places for inverses. So graphically, numerically, what about algebraically? So you probably did this in pre-calculus last year, but let's just do a demo to make sure you're all set. Okay, I have this function here, y equals 3x minus 4. Generally, if you're trying to find the inverse, one quick way of thinking of it is like this. Switch the places of x and y, because remember, an inverse always swaps the x and the y, and then solve for y, and that will get you the inverse function. So let's try that here. So you have y equals 3x minus 4, a linear function. We're going to swap the locations of x and y. So x equals 3y minus 4. And then you just want to solve for y. So let's add 4 to each side. So x plus 4 equals 3y. And divide by 3. Y equals x plus 4 over 3. Or you can do 1/3 x plus 4/3. That is your inverse function. So you could label it as like f to the negative 1 of x. All right, cool. Let's talk about a really important thing you're going to need to know about inverses. You might have seen this last year. I'm not sure. Well, I know you definitely have seen compositions, but I'm not sure if you know this rule about inverses and compositions. So let's take another really well-known pair of inverse functions, x squared and the square root of x. Now, I'm going to call that f to the negative 1 of x. So f and g are inverses of one another. What you can do is you can compose f and g, and a composition, so you can do fog, that means f of g of x, or you can do the other way around, g of f, so g of f of x. And let's go ahead and do that for each and see what happens here. All right, f of g of x. That means I'm going to have f of, what's g of x here? G of x is the square root of x. So then I'm going to do f of the square root of x. So let's plug that in for f here. So instead of x squared, I have the square root of x squared. And that's just x because those cancel. Let's try going the other way. So GOF, g of f of x. So g of, all right, what's f of x? X squared. So now I'm going to take g and I'm going to replace x with x squared. So I have the square root of x squared. And once again, those cancel, you end up with x. Now that is not just a coincidence. That is going to be an important rule that we're going to use when we do derivatives here. If you compose a function and its inverse, you always end up with just x, whether you do f of g of x or g of f of x. It doesn't matter. If you don't end up with x both times, like both ways, the functions are not inverses of each other. So definitely remember this. Let's do one last example here just so you can make sure you're all set here. Let's try doing f. I'm going to make x squared plus 10. And g, let's make the square root of x minus 10. Let's confirm whether or not these are inverses of one another. So anytime you're given a pair of functions and you're asked to decide if they're inverses, just compose them both ways. So let's do f of g of x. So f of the square root of x minus 10. And I'm going to plug that into my function f. So instead of x squared plus 10, I'm going to replace it with the square root of x minus 10. So since it's the square root of the whole thing, that cancels, and you have x minus 10 plus 10, and it works. Awesome. So let's try the other way. So g of f of x, g of x squared plus 10. I'm going to plug x plus 10 into g. So instead of the square root of x minus 10, I'm going to have the square root of x squared plus 10 minus 10. So those immediately cancel. The square root of x squared is x. Check. That means f and g are inverses of one another. All right. That was cool. Let's go ahead and start talking about derivatives and inverses. That was all background information, what you just did. I'm going to go through this sheet of paper. It's kind of a half sheet, a little bit more than a half sheet. And by going through this, we are going to figure out a really important relationship between functions, derivatives of functions, and derivatives of inverse functions. So go through this sheet with me here. Please make sure you're following along carefully and really paying attention to what is happening. I would recommend you pause and try things on your own before I do them. Don't just like mindlessly copy this down or else you're not really going to retain it in your head. Okay, we're going to take this function here, x squared, that we had on the previous screen, but I'm going to restrict it to x is greater than equal to 0. So let's graph f of x using at least 4 points. So I'm just going to do 0, 1, 1 squared is 1, 2 squared is 1, 2, 3, 4. And 1, 2, 3 squared is 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, greater than or equal to 0. So I have my parabola, but I'm only using this half. And there is a reason for that. If I had used all of x squared, then the function would not have been 1 to 1. Like it would have failed the horizontal line test, meaning the inverse would not have been a function. Right now, this passes the vertical line test, which means x squared is a function. It passes the horizontal line test, which means the inverse of this is also going to be a function. And that's what I want. I want everything to be a function. So is this function 1 to 1? Yes. And again, it just passes the horizontal line test and vertical line test. All right, the 0.39 lies on the function. Write this in function notation. That would be f of 3 equals 9. Now we're going to find the derivative. Now this is really important that you're noticing what's happening. We are actually going to find the derivative of f, and then we're going to find the inverse function and the derivative of the inverse. We have to do all those things so you can see the relationship. Normally, we're not going to find the inverse function though, even though you know how to. Normally, you won't be able to, and you'll see what I mean in a moment. Okay, so if f is square root of x, f prime is 2x, that was easy enough. Evaluate f prime at 3, 9. Okay, so that'd be f prime of 3 equals 2 times 3 equals 6. All right, let's pause here. What does this mean? 6, that means that's the slope of the tangent line at x equals 3. So if you were to go to 3 right here, and you can see like this tangent line is going to be really steep here. This is not a perfect tangent line, but again, that looks terrible. But pretend that was a really good tangent line. And I mean, you can just tell by looking at it, that's going to be very steep. And it's up 6 over 1. It has a slope of 6. I'm going to stop trying to draw that now. You know what I mean. Okay, now we're going to go ahead and find the inverse. So find the inverse of f. F, which I'm going to put y, okay? Y was x squared. If I want to find the inverse function, what I can do is I can swap x and y. So now I have x equals y squared. And then just solve for y. So square root, the square root of x is what? And that's the inverse function. So I can call it f to the negative 1 of x. All right, what point on the inverse corresponds to the 0.39 that lies on f? So I didn't really leave myself a lot of space here. But remember, the points swap. So if 3, 9 is on the original function, then on the inverse, it should swap. So we should have the point 9, 3. So 9 is the input for the inverse. Okay, so make sure you're keeping this straight here. 3 is an input for f, and 9 is an input for f to the negative 1. So f inverse of 9 equals 3. All right, now let's go ahead and find, look at this notation here. There's a lot going on. Inverse prime of x. That means the derivative of the inverse function. I think one of the trickier things about this topic is there's so much going on here. You have a negative 1, you have parentheses, you have a tick mark. It can be a little overwhelming notation-wise. We'll talk about how we can simplify things a little bit. So I want to find the derivative of that. Okay, so f inverse of x was the square root of x, which is x to the 1/2. Now let's go ahead and do the derivative f inverse prime of x. Well, I know how to do the derivative of the square root of x. That's not really anything new here. That'd be 1 over 2 square root of x. Now, evaluate your derivative of your inverse at the point on the inverse you found in part f. So I want to find f to the negative 1 of 9. So notice here I inputted, let me highlight it. Here I inputted 3. Here I'm going to be inputting 9 because everything is the opposite in the inverse. So f to the negative 1 prime of 9. All right, let's go ahead and plug that in. 1 over 2 root 9. That's 1 over 2 times 3, 1/6. Whoa, check this out. The derivative of the function was 6. The derivative of the inverse was 1/6. So what do you notice about these two numbers here? You should immediately be able to say that they are reciprocals of one another. And if you can remember that, then you'll be able to do any inverse derivative. Now, there's one other catch here. Okay, you have to be really careful about this. The derivative of the function at 3 was 6. The derivative of the inverse at 9 was 1 over 6. So, like, they are reciprocals, but they're reciprocals at the other number in the ordered pair. And I do want to draw this quick here, just so you know, like, what is happening with this 1/6. So this is saying the slope of the inverse at 9 is 1/6. Let's see if that makes sense. I'm going to try and draw a better tangent line one more time here. Dear God. Okay, so I'm going to graph the inverse. I'll do purple. All right, let's graph the square root. The square root of 1 is 1. The square root of 0 is 0. 1, 2, 3. The square root of 4. 4 is 2. So add this onto your graph. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's hard to see on my screen. Oh my God. So here is f to the negative 1 of x. That's your square root of x. And this was f, which was x squared. Okay, so the slope of the original at 3 was 6. M equals 6 at x equals 3. And what we just found was that the slope at 9 right here is 1/6. So see how shallow that is? So m equals 1/6 at x equals 9. Oh, and you know what? Right here, I kind of like just skipped over that part, but I'm doing it right now, just so you know, like, I did not address this at all until right now. So we just graphed the inverse, check, 4 points, here we go. How should we restrict it? Well, the way you should restrict it, because remember x squared, we restricted it so that x was greater than or equal to 0. Technically, a square root has 2 branches here. We only want y to be greater than or equal to 0. So in order to answer this question here, which again, I'm just getting to now, you want only to plot y greater than or equal to 0. Because if you consider y values less than that, this thing will not pass the vertical line test. All right, cool. So that's all fine. The main relationship is the derivative of a function and the derivative of the inverse function are reciprocals at the other part of the ordered pair. So if one is steep, one will be shallow. Now let's talk about, like, how is this even going to be asked on the exam? I'm going to say this again. I know I already said it. You know how we actually found the inverse function here? Like we swapped x and y. No, where did we do that? Yeah, we actually found the inverse function here in part E. You are pretty much never going to do that on the exam. I always have people who want to avoid using the reciprocal rule and want to just go ahead and find an inverse function and do a derivative. But you're often not going to be able to do that. Like right here, look at this question. Classic multiple choice question from 2015. You're not even given the function's equation. So there's no way you could actually find an inverse of it. So you're going to have to use the fact that a function and its inverse are reciprocals. I'm going to show you 2 ways how to do this. I do prefer one of the ways over the other, but you are free to use whichever way you want. The first way, is going to be strictly using ordered pairs and the reciprocal relationship. Another way is using a formula. When some people really like using the formula, you just have to remember what it is, but it's really quick to derive. I always, no matter what step or like what method you use, I always recommend setting up ordered pairs. I actually struggle to answer these questions if I don't have my order pairs written down because I like to see that visual. Okay, so can you jot yourself down this table here? Pause quick if you need to. And So it says the table above gives selected values for a differentiable and decreasing function f and its derivative f prime. If f to the negative 1 is the inverse function of f. So what is this thing even asking? This wants the derivative of the inverse at 2. Now they didn't use g here. Sometimes they call the inverse g, but they didn't in this case. We're just going to call it f to the negative 1. All right, so one thing you have to remember is this 2 is an input of the inverse. So I'm going to put that here. If it's an input for the inverse, it's an output for the function. So let's go ahead and fill in our ordered pairs. So look at f. What's the x value that has a y value of 2? Well, here's f. Here's a y value of 2. The x value is 1. All right, so that means the inverse will have the ordered pair 2, 1. So, again, always do this. If you set this up, then visually you're going to be good to go. Okay, so this is how, again, I typically do this here. What we want in this problem is we want the derivative here. We want the derivative of the inverse at 2. That is what this is saying, derivative of the inverse at 2. So what we're going to do instead, because again, I don't have an inverse function. It's not like there is a column labeled f to the negative 1. That doesn't exist. What I'm going to use instead is we're going to find the derivative here. Okay, so that means I'm going to do f prime of 1. And I can use my table, and I'm going to find f prime of 1, which is negative 8. And remember, the relationship is if the derivative of the function at 1 is negative 8, that means the derivative of the inverse at the other part of the ordered pair, which is 2, is going to be the reciprocal, which is 1 over negative 8, which is the same as negative 1/8. That's how I think about it. I write down the derivative, and then I just flip it to be a reciprocal. So I'm going to show you another way that people do this sometimes. They use the fact that if two functions are inverses, and we're going to let g be the inverse of f. You know that f of g of x is going to be x. So let's go ahead and actually do a derivative of each side. I'm going to do a derivative of that, and I'm going to do a derivative of that. So how do I do a derivative of f of g of x? Well, that's the chain rule. It'd be f prime of, don't touch the inside, times g prime of x. And what's the derivative of x? It's 1. And remember, what we're looking for is the derivative of the inverse. Well, the inverse is g, and the derivative of g is right here. So in order to get that alone, if you just divide by f of g of x, f prime of g of x, that cancels, and here is the formula that you use. And some people, some videos, some professors, etc., will just plug right into this formula. So let me solve this problem by just using this formula here. So this is how it would go. It would say g prime, and remember, g is the inverse. You have to remember that. So g prime of 2 is going to be 1 over f prime of g of 2. And let's go ahead and simplify. So that'd be 1 over f prime of, start on the inside, g of 2. So g is your inverse, and g of 2, the input of 2 in the inverse, has an output of 1. I'm just going to get that right from my ordered pairs here that I already wrote out. So g of 2 is 1, right there. And then 1 over f prime of 1. So the derivative f prime at 1 is negative 8. So you don't ever really have to think about a reciprocal because the reciprocal is already built in because the formula is already 1 over something. All right, let's run through one more example real quick. And then you're definitely going to be ready for this video to be done. Sorry, this one was a little longer than I intended, but I just want to do one more example so fast. Okay, here we go. Ordered pairs. So f, I'm going to call g the inverse. So g is f to the negative 1. Ordered pairs, here we go. All right, I'm going to let my function be this. Now, you don't want to deal with the inverse of this. We're not actually going to find the inverse function. We're going to use the reciprocal relationship of a function and its inverse's derivatives. So you're just told here 1, 3 is on the graph of f. Bang, put it right in your ordered pairs. Immediately, bang, inverse function is 3, 1 because they're flipped. Now, what are we looking for here? We're looking for g prime of 3. That's the same as saying the inverse derivative at 3. So this is how I'm typically going to do it. I'm going to say, hey, look, I really want the derivative here, but I don't really have my inverse function, nor do you need to find it. You're going to go right above, whoop, and you're going to do the derivative here instead. Because like you have the function f, you can do the derivative there. So let's find f prime. That's an easy derivative. That'd be 3 plus 1 over x. I'm going to do the derivative at the other part of the ordered pair. I want the inverse derivative 3, so I'm going to do the derivative of the original at 1. Okay? So that'd be 3 plus 1 over 1, which is 4. So that means the derivative of the inverse at 3 will be the reciprocal, 1 over 4. And it's really important that you're practicing good labeling here throughout your work. Okay? I'm going to show you the other way here in case you want to use it. So I'm not going to derive it again. I'm just going to use that formula here. The derivative of the inverse is 1 over f prime of g of x. So the derivative at 3, I'm going to plug 3 in. All right, so g prime of 3 is going to be 1 over f prime of, what is g of 3? According to my ordered pairs, g of 3 is 1. And then we kind of already did f prime of 1. But if you were doing this method, you would find the derivative and plug 1 into it. And f prime of 1 is 4. So again, the reciprocal is built into the formula already. Yay! All right, cool. So we're going to practice this in class. That is all. See you later.